So off to our last and final section for chapter 3, and what we're going to be looking at is yet another radian application that relates to speed. So let's go ahead and first address the two types of velocities or speeds that we're going to talk about, and then in another video I'll basically show how these are related, and they have very many applications, as you guys will see, in physics and in science and math and everywhere else. But as far as the velocities are concerned, the two types are linear velocity and angular velocity. So when we look at these, linear velocity is probably the one you're most familiar with, because we have the old distance equals rate times time problem. And so when we basically divide both sides by t, we end up with the rate being the distance over time. So distance, divided by time, right? That is basically our speed, right? So how fast we go. So usually what ends up happening is, to find our linear velocity, right, we're probably talking about miles per hour, right? So the distance I travel in miles over the number of hours that it took me to travel that, right, would give us our speed. So my distance in miles divided by my time. If you're a track athlete, you probably are used to meters per second, because again, the distance we traveled, we maybe went 100 meters, and then it took us so many seconds to do that. So under this formula, right, take the distance that you traveled, divide it by the time that it took you to travel, and you get your speed of travel. So miles per hour, meters per second. I think another one that we see a lot in physics and whatnot is feet per second. So it's basically always some unit of distance, meters, miles, feet, kilometers, whatever the case might be, divided by some unit time, which are usually in seconds, minutes, or in hours. And so that's basically how we calculate linear speed. One thing that will change, kind of starting to make the connection, is when we start looking at a circle, all right, when we rotate through some angle theta, as we've learned, what we've done is we've swept out some arc length. Let me change colors here. We've swept out some arc length along the edge of the circle. This is basically our distance traveled, all right, in terms of a circle. So how far we traveled as we rotated around, the distance that I traveled, right, is the arc length that we occurred, and we've called that S. So what you'll start to see is the formula for speed, right, will be V for velocity, right, our speed. Our distance is going to be called S, and our time is going to be called T. So some new terminology there, rather than D's, R's, and T's. The velocity linearly is this curly cubed V. The distance we're going to travel we're going to call S, because we're relating it to an arc length along the edge of a circle. So the distance that I travel is from this point on the circle to this point. That's what we call arc length. So we're going to continue to call that S. And then the time of travel, that's probably the only variable that stayed the same, is time. So linear speed is basically the distance that we travel over the time that we travel. So with regards to applications, in the first example, Usain Bolt, who happens to be the fastest human being on the face of the planet, we know that he ran 100 meters in 9.58 seconds. So basically, how far is that, right? Well, his linear speed, right, is the distance that he traveled over the time of travel, all right? And so in this case, the distance traveled is 100 meters, and the time of travel was 9.58 seconds. Alrighty, and so basically what we have, right, is his linear velocity. Now, of course, going to a calculator, I'm just using something really quick on my computer. 100 divided by 9.58, right, gives us 10.4384 meters per second. So that would be his linear speed for the 100 meter dash that he did in Olympics a while ago. Okay, so again, I guess I should have written this as S over T as well. All right, although in this case, the linear distance is truly, right, a straight line distance, not an edge along a circle, but it's still distance. So he traveled 100 meters in 9.58 seconds. So we've calculated how fast he was going in meters per second. And the next one, I will relate it to a circle. What we have here is we have a central angle in a unit circle sweeps out an arc length of 4 feet in 3 meters. All right, so unit circle meaning that we have a radius of 1, arc length meaning with my distance traveled along the edge. So let me try drawing a picture here. All right, so our radius is equal to 1, and what we're doing is, let me change colors, we're going to sweep out an arc length of 4 feet. All right, so 1 foot, 2 foot, 3 foot, 4 foot. All right, so just kind of hypothetically speaking, we've swept out a distance of 4 feet along the edge. All right, and so what we end up getting, right, in terms of speed, the velocity is my distance traveled over time. In this case, my distance traveled was 4 feet, and the unit time was in 3 minutes. So basically, this person traveled, or we're traveling on the edge of the circle at 4/3 feet per minute. All right, so that would basically be our linear velocity along the edge of this circle, right? If we had a, and by the way, there's the angle that we have, right? So we really don't know what that angle is, although we can find it, right? Theta would be 4/1, so it's 4 rad. All right, so if you had to find the central angle, there it is. So we have a unit circle, so it's 1 foot. We went 4 feet along the edge, so 1 goes into 4 times, giving us a central angle of 4. But really not needed here, because we just need to know the distance that I traveled along the edge divided by the time gives us our speed, all right, linearly. So how fast I was moving in a linear fashion along the edge of the circle. Alrighty, so how about that we're 7 minutes into linear velocity. Why don't I cut away and we'll come back and do angular velocity in a video coming soon. Talk to you guys in a moment.